Today we're going to talk about oxidation reduction reactions, or more commonly referred to as redox reactions. These are very important type of reaction in chemistry, and we'll deal with them throughout the year. So what is a redox reaction? Well, a redox reaction involves a transfer of electrons. A very simple redox reaction is a combination of sodium ion with its one extra electron to the chloride, or from the sodium atom to the chlorine atom to produce the sodium ion, positive, and the negative chloride ion, that combine to form sodium chloride. So since this was involved in a transfer of electrons, we see that this would be classified as a redox reaction. Most are not going to be this simple, so we have to have a way to determine, do we have a redox reaction? And the way we do that is we assign oxidation numbers. And there's some rules for assigning them because they are a bookkeeping strategy that we use. They don't physically assign electrons or mean the assignment of electrons, but they allow us to keep track of where the electrons are coming and going. And so once we assign oxidation numbers, we see that if we have a redox reaction, some of the oxidations or numbers are going to change from the product, or from the reactant side to the product side. We always have oxidation, meaning the oxidation number is going to increase in pair with reduction, meaning there has to be oxidation and reduction. And we'll get more into that after we learn how to assign the oxidation numbers. To do that, we have some rules. These may seem complicated at first, but as you practice them, they become much easier, and you don't have to refer to them all the time. Our first assignment is that any uncombined element is zero, meaning if we have H2 plus O2 producing H2O, we have H is uncombined, even though they are the diatomics, and I perhaps shouldn't have used both diatomics here, but no. These are both diatomics, so we assign the oxidation number of 0. Our usual method is to sort of write above the element the oxidation number when we're assigning them. So these are uncombined. Likewise, as in our first equation on the first slide there, we had this equation, so sodium is uncombined and chlorine is uncombined. One also knows we're assigning it for each atom. That means each hydrogen atom, even though there's two of them, has an oxidation number of 0. We don't total them up, even though in this case 0 plus 0 would be 0, but we'll see more of that as we move along. While this is kind of the easiest one, it's often the one forgotten when you're starting and doing these early on. So always note when you have an atom that's in its elemental state, meaning either as an atom or the 7 diatomics that we have, as in hydrogen and oxygen and the others, those always have an oxidation number of 0. Okay, well, we've got two rules coming up here, so let's look at both of them. The second rule, a monatomic ion equals the charge of the ion. So meaning if we have an equation that's monatomic, we don't want to use fluorine there, but if we have let's say magnesium, combining with oxygen, make magnesium oxide, but we see that magnesium here has a 2+, so its oxidation number is a 2+, or we could write +2. Either way is going to be fine. I guess usually we would put the plus sign here and after for the ion. And just going back to rule 1, since O2 is that, we would assign that an oxidation number of 0. Okay? Fluorine is -1, whether it's fluorine as a monatomic ion, that would also qualify as the second rule there, or if it's part of any compound. Okay? And assigning them in this compound is where we get into a little bit more tricky. So here in HF, okay, we had HF plus, I don't know, NaOH. Okay, we would assign the fluorine a value of -1. Our next rule is oxygen is -2. It's usually -2. Here we have a couple exceptions. Okay, so our exceptions are unless it's combined with F, okay, when it is a +2, or it is in a peroxide such as H2O2 when it's -1. All right, so let's look at some examples. So if we're looking at water, okay, we're going to see that the oxygen is assigned -2. If we're talking magnesium oxide, it's -2. If we're talking sodium hydroxide, okay, our O is still a -2. Okay. And this is going to be the case for almost everything. So if you can't remember the exceptions, okay, and nothing else is working for you, meaning we're going to get to some other rules where you might be able to identify what it is, just assign it a -2. Okay. Compounds where you're going to see it with combined with F are like OF2 or something similar. There may be some other compounds. These aren't very common in our course this year, but in this case the oxygen would be a +2. And peroxides, okay, the peroxide ion, which you should probably know from your ion list, is well, we make something like hydrogen peroxide. Okay, we have this is going to be a -1. Okay. So some other peroxides, sodium peroxide. So how do I know it's a peroxide? Well, I look and I know that typically hydrogen is combined with 1 oxygen. Okay, here it's 2 and 2. Likewise, sodium in a typical scenario with oxygen would be N2O. We see the N2O2 tipping us off that we have this peroxide ion, meaning it's going to be -1. Again, hydrogen peroxide, relatively common, okay, although we don't see it that often in that many equations. So if you can just recognize a few of the common peroxides like H2O2, sodium peroxide, somewhat. Okay, the group 1s with a 2 and a 2 are the most common. Our next rule is hydrogen is +1, except when combined with a metal. Okay? It's similar to oxygen, is we're almost always going to be our +1. Okay? We see here hydrogen, we also have our rule for oxygen, -2. Okay? We could look at the peroxide, which was again our exception in the previous rule. Hydrogen still +1, but here we have the exception for the oxygen or peroxide ion. So when combined with a metal, we look at things like lithium hydroxide or lithium hydride, sorry, or sodium hydride. Again, these are going to be -1, not very common either. We have some other ways to double check this on our upcoming rules too. So again, there's a lot of different ways we can go about these, and if you have troubles with the exceptions, then just kind of try approaching them from a different rule or standpoint, and you may be able to solve them. When we look at some examples, maybe that can help you. Okay, our next rule is that all group 1s have a +1, group 2s have a +2, and aluminum has a +3. So these are just like our ions, right? Sodium, and if we go sodium hydroxide, we know sodium's a group 1, so it's going to have a +1. And these are always, there are no exceptions. Okay, so we also know that oxygen is a -2 and hydrogen is a +1. So we now have rules where we can give all the oxidation numbers for those. So group 2, like magnesium, fluoride. Okay, magnesium is group 2, so it's going to be a +2, and fluorine is always -1. Okay. So if we look kind of at the last one where we were talking, well, we have sodium hydride. What if I don't remember that hydrogen is a +1? Well, we know sodium, or a -1, we know sodium is a +1. We're going to see a rule in just a second that will let us solve this. So we're going to come back to that, but knowing that sodium is what it is, we're going to be able to identify that the hydrogen has to be -1 in this case, as one of those exceptions. Okay. This next rule, the big rule, or one of the big rules, the sum of the oxidation numbers of all the atoms in a compound is 0. Okay, so we look at copper oxide. Well, we don't really have any rules for copper. Okay, it's a transition metal. Okay? There are lots of elements that have many different oxidation numbers. And if you look on some periodic tables, they will list the different available oxidation numbers. You probably saw in previous chemistry that copper can form different ions, and likewise it can have different oxidation states. So the transition metals we have to solve. Okay? Well, we know oxygen is -2. Okay? Well, what we also know is that the sum of all the oxidation numbers has to equal 0. That's what this rule says. Okay? So if we assign copper an oxidation number of X, we can just solve for it. So we have X plus the -2 from the oxygen equals 0. So we easily see that the copper, okay, has a +2 oxidation number. Okay, if we look in a little bit more complicated one, okay, we see sodium is a +1. Okay, our rule said group 1 metals are +1. Remember, as I said earlier, even though there's 2 of them, we still just write a +1, but we will account for each of those later on. Okay, sulfur is another one that can have many different oxidation states. Okay, oxygen, again, -2. Okay, we did know there were some exceptions to oxygen, but that was with fluorine or in a peroxide. This isn't either. Okay, so sulfur we don't know, and we're going to assign X. Okay, so we do need to calculate it now. Well, we know that this is sodium, each sodium is a +1, and we just multiply it by the 2 because there are 2 sodium atoms. Okay, we have X, there's only 1 sulfur, so it's just 1X. Each oxygen is -2. There are 4 of them, so we multiply that by 4, and we solve. And so we get 2 plus X plus -8 gives us 0. So our X equals a +6. So our sulfur oxidation number in this case is a +6. Okay. So that is how we get a lot of our oxidation numbers. We use our rules to solve what we know, and we solve the missing ones based upon the fact that for a neutral compound, the sum of our oxidation numbers has to equal 0. Okay. If it's an ion, okay, the ion charge has to equal, or the oxidation numbers has to equal the total ion charge. If it's monatomic, we already kind of saw this in the rules that, right, chlorine has a -1 charge, so it has a -1 oxidation number. So this was really covered in the previous rule. But if we look at a polyatomic ion like nitrate, we see it as a -1 charge. But just like previously, we can assign oxidation numbers. We know oxygen is a -2. We don't know nitrogen. There's no rule for it. It can have lots of different oxidation states. We calculate it. There's only one nitrogen, so it's 1x. There's 3 oxygen. Each oxygen is -2. The total, instead of 0 now, is a -1 because that is the charge of the of the ion. And we just solve when we find that in the nitrate ion, our oxidation number for nitrogen is a +5. Okay. And so this is just a summary of all the rules that we just went through. Now let's look at a couple practice problems. So what is the oxidation number of potassium in K2Cr2O7, which is potassium dichromate? Okay. Well, do we have a rule for potassium? Because that's what we're looking for. Okay. Well, we do. Potassium is a group 1 metal. Okay. So it has to have an oxidation number of +1. Okay. So A is the answer. Okay. Well, looking at the same compound, looking at oxygen, do we know the oxidation number for oxygen? Okay, our first thought to ourselves should be, is there a rule? Yes, there's a rule for oxygen. It's usually -2. There are a couple exceptions. Okay, is this in a peroxide? No. Is this combined with fluorine? No. Okay, so we know the oxygen has to be -2. Okay, so that's going to be, C is going to be our answer. Chromium. Okay. This time, okay, do we have a rule for chromium? Well, chromium is not a group 1 or group 2, nor aluminum. It's a transition metal, so we don't have a rule for chromium. But as we saw previously, we do have rules for both the potassium of +1, the oxygen -2. So now we have to solve. We have 2 times the +1 plus 2 times x, right, with chromium being our x oxidation number, and there are 2 chromium atoms, plus 7 oxygens in this case. Each one of those is -2. The sum of those has to be, yes, 0 is correct. We do all our math. We get 2 plus 2x plus -14 equals 0. And we solve, and we get what? That is correct. We get a +6. Okay, so our chromium oxidation number equals +6 in this case. And that is oxidation numbers. Here's another question. In which substance does chlorine have an oxidation number of +3? So what's the oxidation number of chlorine here? Is it +3? I want to say Cl2. What is it? It's alone. It's an elemental state. That means the oxidation number for chlorine in this case is 0. Don't get caught up thinking that's -1. Again, elemental state, 0. And in this case, all right, our hydrogen is a +1, so our chlorine is a -1. Okay, so that's not a +3. Here again, hydrogen +1, oxygen -2. Okay, solving for chlorine, we have +1 plus x -2 has to get us to 0. So chlorine is, that's right, a +1, which means D must be our answer. But let's check it out. +1 -2, but this time there's 2 of those. So we have a -4 plus 1. So our x in this case must be a +3. And that is our Oxidation numbers. We'll next look at what we do with those numbers in identifying redox reactions and identifying what has been oxidized and what has been reduced.